Okay, so next on the agenda we have John Kaitschuck. He's Senior Staff Engineer at Seagate Systems and Silicon Group. Previous stints at Cray, NCAR, NERSC, LB&L, ILM, General Motors Research. At Seagate, he deals with Lustre performance, various other interesting issues as assigned by his management. That sounds familiar. Ladies and gentlemen, presenting John Kaitschuck.
Okay, I'm here, pardon me, I'm here today to talk about fragmentation and capacity on Lustre file systems. And I'll move through relatively quickly here because we've got quite a few slides to get through. So this is our agenda, a little bit of history and background, some focused. The test environment we're using in Seagate to test some of the study we're going to be talking about, our nomenclature methodology, choices we've made, some of the results, lab versus production, and observations, and then a conclusion. All right, so if you look into your file systems literature, your computer science literature going back 20, 30 years, you'll see numerous papers around fragmentation. I've got papers that date from the late 80s, early 90s, and I'm sure there are more further back in time if you go back far enough. In a nutshell, standardized way to generate and test file system fragmentation doesn't generally exist. There has been some previous performance work in Lustre with file system fragmentation, but a lot of this work was incomplete related to our needs at Seagate. We did run across a couple instances. Our first instance with ClusterStor, which is our product to report impactful fragmentation encountered at scale, dealing with a metadata performance issue. And we decided to dedicate resources in our Fremont lab to study this and to see what we could come up with. Okay, so our focus for this study was, given limited resources and time, try to formalize methodology to study capacity and fragmentation, gather as much data as we possibly could to relate the performance impact of fragmentation and bandwidth, produce as much information as we possibly could to inform our customers and also to share with the wider Lustre user community. And if at all possible, look at instrumentality and determine if the data proves that this is impactful enough to determine what might need to be done with instrumentality going forward in time. So here's our test environment that we used in Fremont over a 2-month period of time. We had 16 Intel clients running Lustre 251 client side, Trinity 200 with a ClusterStor 5U84, which is what we call a storage, scalable storage unit, an SSU. +0 means there's no expanders on the back. And you can see the client side parameters we were using. All these things were kept relatively constant in our testing, and then we were using Megalodon disk drives, which we had available in our lab. So when we talk about population and fragmentation, there are numerous ways, if you think about it, that you could populate and fragment a file system. So we came up with this nomenclature. And this nomenclature basically allows us to write things down for the way we're testing things in the lab. So we call it PAF, P-A-F, which stands for populate and fragment. And you can see here at the bottom where it says Gen 1 non-deterministic homogeneous, all the way down to Gen N deterministic heterogeneous. And by homogeneous, we mean a file system data structure that's made up of all the same size files. By Gen 1, we mean we want to make one pass, and that's where most of our testing has been focused thus far. Non-deterministic means we're using a pseudo-random way of selecting what files we remove in the data structure to fragment the file system. And this goes from what you see at the very top all the way down to a Gen N deterministic heterogeneous sort of generation for testing, and that's a much more complicated way of forming fragmentation. But you could do that given enough time and resources in whatever lab facility you have. So there's a limitation on how we're generating population and fragmentation in the laboratory today. Our actual usable capacity within the file system is higher at higher fragmentation levels. You'll see that in a minute or two. While this allows us, the simplistic method allows us to collect more data in a shorter period of time, it doesn't represent the possible worst case scenario. So if you've got a Lustre production file system and you run it for 12 months and you've had numerous people running their applications, removing files, and the files are all different sizes, and they fragment things, and you run your capacity up to 80%, and then you look the next week and you're back down to 60. I can assure you what we've done in the laboratory here does not represent the worst case scenario you could get into in the real world. And it doesn't represent an imbalance in target utilization. So we have 2 OSTs in our simple lab setup. We don't have 300, 400, 500, 1,000 OSTs. We don't have imbalance where one OST is at 20% utilization, another OST is at 80% utilization. We haven't tried to model that with what we have today. And while fragmentation may be a contributing factor to performance degradation in a production environment, it's not the only factor. If you're using hard disk drives and you have remedial drives and you have a large number of OSTs, you could have a problem. Anyone who's used InfiniBand knows that InfiniBand cables can be extremely brittle. That's potentially a problem. So there's a lot of things in a typical Lustre file system configuration in most environments where you can have a lot of underlying elements that can cause you performance issues. You should be aware of that going in. So what's our methodology? Our methodology for how we populate and measure for this study. So we've broken it into 2 phases. Phase 1 you see here on the left is we use a utility called Brinzel, which is a proprietary utility we have within Seagate to populate and fragment the file system. We basically populate the file system up to a given percentage of utilization, and then we fragment the file system by removing select files. If we were doing a multi-generational pass, we would do that multiple times, but all of this is focused on a Gen 1 pass. So in a Gen 1 pass, we populate, we pseudoly randomly remove files from the data structures that are created at population time, and then we use IOR, which is a relatively standard HPC utility, to measure performance impacts across a wide range of variables. Most of the time we are focused on 16 nodes and 16 tasks per node, and we're holding everything constant except for changing transfer sizes. After we're done doing 5 iterations and we record those 5 iterations, we take the mean value of those 5, we then scrub the file system, we remove everything, we repeat. So rinse, wash, repeat. We do this multiple times to different file system capacity levels to see what the curve may look like. So here's a very simple example of us populating a file system. So we create a data structure. That data structure is composed of a set number of directories mounted to the very top mount point we have, and then we have a certain number of files that are populated within the directory structure, and we move from the top down. Now this is a very simple example. In the case of the data structures we were creating for actual measurements, we were creating data structures that were much larger than what you see here. But this is what would fit on a slide to show you how this is done. Our execution flow is from the very top to the very bottom as we create these large data structures and then populate them with files. So that's what it looks like in our very simple example here once we're fully populated. We have, you can see it's what I call a symmetric data structure. So we have 1 directory at the top, 2 child directories, and 2 children underneath it, same number of files in each directory. And then to fragment this on our first Gen 1 pass, we start at the bottom and we pseudoly randomly select files within the structure to remove, given number of files in each subdirectory. We remove those files, you can see they're crossed out here, and we flow up from the very top, from the very bottom to the very top. And what you end up with is a fragmented file system, represented here, real loosely, by the fact that we have this directory structure with a certain number of files, and you can see the files that we removed have been grayed out. But we've basically fragmented what we're doing. So we've made a variety of choices here for how we do this. Like I said, we're pseudoly randomly removing things, so it's non-deterministic. This provides a wider range of coverage for our baseline. You'll see a little bit later that we're doing several thousand test cases. So ideally, when we do things pseudo-randomly, if we do several thousand samples, we should end up with a good, wide statistical sampling. It's Gen 1 homogeneous, and by homogeneous, all the files that are in that directory structure that we're creating, or those directory structures, are all the same size. They're not what you would get in a real production environment. They're all given file size. We do that because it's quicker to cover the data, to generate the structure, than to try to do things with a lot of variation. We're using a 10% fragmentation spread, and we're using a 10% capacity increments because, again, we're trying to create a very rough baseline versus the amount of time we can actually dedicate in the lab to do this. We use Brinzel because it's a threaded code that scales to the number of available clients. It uses MPI with barriers, and it uses POSIX.io to generate all the data structures. And then if you look at this related to our nomenclature, we end up with a statement that says path AA BB at 264. So on the far right, to the right of the less than sign, you see the total usable capacity of the system when it's unpopulated. AA would be the percent we populate the file system up to, whether that's 10, 20, 30, or 40. BB would be the probabilistic fragmentation factor we use to remove files from the data structures that populate the file system. And the fragment size or the file size that are in these data structures is homogeneous, and in this case, it's 264 megabyte files. If we had multiple instances of different file sizes and it was heterogeneous, we would write that shorthand 264M, 33M, 16M, so forth and so on. So if we do this for our Series 1 performance, we run 8 different population and fragmentation capacities from 10 to 80%. We run 8 different degrees of fragmentation from no fragmentation at all the way up to 70% fragmentation. We're doing 7 transfer sizes from 1 megabyte to 64 megabytes. We're using direct I/O for 98% of our testing here. And the reason we use direct I/O, I should point out, is if you're trying to diagnostically confirm what's going on in your Lustre file system, and you've got a series of clients, you're much better off using direct I/O and bypassing buffer cache for repeatability. You can use buffered I/O to try to diagnostically do things, but it typically takes a larger number degree of iterations. And in the lab, we're trying to minimize but get results as quickly as we can. What we end up with is 2,240 result pairs composed of direct I/O reads and writes across those variables. And again, this is where our shorthand notation from 10 to 80%, from 0 to 70%, 70% probabilistic fragmentation, 264 megabyte files against the file size, the OST sizes that you see there. So we've had people ask us in the past, what does it mean when I run my file system up to a given capacity? If I'm at 50% utilization, how does that affect performance? If I'm at 70% utilization, how does it affect performance? You see 2 curves here. The top blue curve is 64 megabyte transfers using direct I/O. And you can see that as you get much beyond 50%, 60% utilization, you start to get to what I would call the black diamond sort of effect. If you're a skier, you know what that means. You get a drastic decrease in performance. The 8 megabyte transfer line is roughly equivalent to that. You see the dip in, these are only writes, you see the dip, the dimple around the 40% capacity mark. That's because we had a drive in our lab go bad and the OST start to rebuild when the test was running. Typically with Lustre, you can set the min sync, max sync rebuild rate for how much dedicated bandwidth you use. But since we ran this for roughly 8 weeks at a variety of different test cases, if I recall correctly, that was about at 1:30 in the morning, and there weren't too many people around to say, oh, the drive has gone bad. We should stop things and replace it. But you can see the effect of purely a capacity. This is without fragmentation. We haven't fragmented the file system at all. We've only populated it. We've kept writing and writing up to a given percentage. We do a series of measurements to get our values, our 5 iterations from IOR, and then we populate some more. There's no fragmentation here, so that's not very realistic in most real-world scenarios that I'm aware of, but we've had people ask that question. And here you can see the relatively, pardon me, the same effect on reads. Again, our dimple, where our drive decided it was going to have some issues, but you can see roughly the same effects for 64 megabyte transfers and 8 megabyte transfers with direct I/O. If we look at the percent of variation for what I just showed you, our coefficient of variation for our 5 measurement points at different capacity points from 10 to 80%, our coefficient of variation is very good. Even in the worst case scenario, the far right side of 80%, we're slightly less than 3.5% variation between our 5 measurement points. So I'm reasonably pleased with that. So what does this look like when I start to fragment the file system, and how do we represent it? So what we've done with this next graph is we've created a 3-dimensional surface. This 3D surface, you can see Gen 1 capacity running from the middle point of the graph up the, I believe you would call it the x-axis. Maybe I'm being dyslexic here. X-axis being Gen 1 capacity, y-axis being fragmentation, z-axis being megabytes per second. So on the far left side, you can see that we're getting not quite 9 gigabytes a second. That's a perfectly clean, pristine file system. There are no data structures, there is no fragmentation. If you ask a vendor to benchmark a file system for you, that's what you're going to get, the far left corner of that graph. The reality, good, bad, ugly, or indifferent, when you're using hard disk drives, is you're probably off someplace in the valley off the mountain there. So you can see as we get up to a fragmentation percentage of around 20%, at about 40% Gen 1 capacity, you can see you start really hitting the slope of what performance you get. Because of the way we're modeling fragmentation, as we free up more and more space, and again, this is writes only, but as we free up more and more space and then end up at the roughly 70% down at the far right corner, you can see that we get a saddle sort of effect. So the graph starts to bend upwards. Our surface starts to bend upwards. That's because as we increase fragmentation, we're freeing up more and more space. That allows you more and more empty holes to write new files. So it becomes much easier to write files. Our heads don't have to seek as often. Interestingly enough, obviously, this is all direct I/O with HDDs. I hear you say, but what if I use SSDs? What if I use an all-flash array? Feel free. You won't get this effect. You might not be able to afford 5 petabytes of all-flash array, and you have other issues with all-flash arrays. All-block storage has some limitations, whether it's disk drive head movement with trying to deal with fragmentation, or if it's all-flash array SSDs with limitations on the number of writes you have plus the combined cost. All block storage of some form or another has some limitations you need to be aware of when you design your file system or when you buy your file system from a vendor. If we look at writes, we don't see hardly any noticeable impact to fragmentation, or pardon me, if we look at reads, we see hardly no impact to reads with fragmentation that we did with writes. We basically had a customer confirm this on a small system in the field, a small R&D system they have. So they were seeing the exact same effect. If we look at this with smaller transfer sizes, and here we've taken a slice, so if we go back out here, we've taken a slice at roughly the 20% capacity point, so we've sliced through our graph. And here it is with different transfer sizes. So if you're using a smaller transfer size, let's say your customers or your application is doing 4 megabyte I/O transfers, it isn't as noticeable. But that's with 256 megabyte, or pardon me, that's with our standardized 264 megabyte fragments. We haven't varied the fragment size. But you do see a slight dip. You see more of a dip with 8 megabyte transfers, and you really see the effect with a 64 megabyte transfer using IOR. So we looked at Series 2. We keep everything constant, but we vary the fragment size. The file size we change in the directory structures we're creating, and then we remove them. So in this case, we would go to using a 33 megabyte file size. And here you see The same line that you saw before, 2 lines, a 64 megabyte transfer, blue line, 64 megabyte transfer, brownish orange line. One is 264 megabyte fragments, the other one is 33 megabyte fragments. As we've decreased the fragment size, the impact has remained essentially the same, only it occurs at a much higher velocity, if I can use that word here, at a lower percentage of fragmentation. You can see the dip is lower at the 10 and 20% marks than you are at with 264 megabyte fragments. And obviously, again, this isn't a lab. I don't think too many people would have a real world application where your files are all the same size. There are some exceptions, I could think of that, but a lot of real world applications wouldn't be like this. So our problem is this. We can do this in a lab, but what does this mean to a production environment? What does it mean to a real operational environment today? So how do we estimate the degree of impact of fragmentation to production sites? If you've got a production site, whether you're a Seagate customer or not, and you say, well, how bad's my fragmentation? Today, I can't really tell you. There's some tools we can use, and we'll discuss those in a moment, to try and get a handle on what you're seeing, but it's a little bit difficult. The instrumentality is problematic in production facilities, and the bigger your production facility is, the more problematic it becomes. So we've got 2 possible approaches, block traces and Dumpy 2FS. And I'll show you examples of both. But we're assuming, in this case, that all else is optimal on your site. Your OSTs are happily balanced, your HDDs are all fine. Whether you have 200 or 2,000, they're all perfectly happy. And so let's see block trace example. So we went out and we did block traces on our targets. And on the left-hand side, you see writes on the upper left corner, you see reads on the lower right left corner. That's without fragmentation. When the file system is fragmented, on the right-hand side, above for writes, below for reads, you see the effect of fragmentation on block traces. And you'll notice an interesting thing here. I call it the deflection curve. If you trace along the floor of the graph, along the floor of the heat map on the fragmentation side, you see this kind of curve effect for the displacement from, and you can't see it, but it's basically the capacity range. You see a displacement where the heads are moving. So that the heads have to seek out further in capacity range. So you probably say, that's the way I know how much fragmentation I have. I'll just kick off block traces and I'll start looking at it. Okay. Let's talk a little bit about that. So block traces can provide circumstantial evidence that you do have fragmentation on your file system. But if you've got 500 OSTs, I don't know that you want to collect block traces for all 500. It's also a little time intensive to do this analysis. So in Seagate, our core HDD people, our disk drive people we work with in the SSG group, were very good to help us out in doing the analysis and doing the heat map for us in this particular case. But it's time intensive to do that. It also assumes implied knowledge about your workload. So let's say you run block traces for 24 hours in your production facility. You better know what's going on for all 24 hours. Some places can tell you every job that's ran in the last 24 hours, and maybe they have a batch system, maybe they're running interactively. Other places don't have that luxury. So you have to be able to know precisely what was going on. The following jobs ran in the 24 hours while I was doing a block trace. And again, this is non-optimal. I can't see doing it for 500 or 1,000 OSTs. Cool if I'm in a lab and I got a few OSTs and I want to play with this concept, but it's a little difficult. Dumpy 2FS. So you're probably well aware, Linux has this wonderful utility. You can run it on a live file system called Dumpy 2FS. You can run against your OSTs. Provides basic group allocation, can be invoked on each OSS, can be run while the file system is active. Yay. Header and group allocation information just dumped right out in a file for you. And sometimes you see this used in conjunction with other utilities like FileFrag, eval, Dumpy 2FS, whatever. But it produces copious amounts of data. And by copious, I mean 390 megabytes per OST. So again, you got 500 OSTs, good luck. This is what it also looks like. So you look at this and you don't have a way of mapping this readily back to what you're seeing as far as, does this mean I lose 10% of my performance? Do I lose 20% of my performance? How much do I lose? And we at Seagate are trying to go through that exercise right now, but this needs much further refinement, Dumpy 2FS to the data for your actual product. If you're using a Seagate product, it might mean one thing. If you're using a DDM product, it might mean something else. If you rolled your own version of Lustre and you're using disk drives from whoever, it could mean something else because you don't have that baseline, that family of characteristic curves to map this against. You have to have a good understanding, at least to a certain degree. So let's talk a little bit about observations. So a simple OST fragmentation model in lab can cause up to 35% data loss of bandwidth. That's at very low utilization percentages. Most model fragmentation is highly impactful on lights and less so on reads. Fragmentation can contribute to loss of performance at Lustre and Cluster Store, and it's not just Cluster Store. I'll kick my own product because I'm with the vendor, I'm allowed to do that. But I can assure you have this issue every place else. This is LDiskFS, folks. This isn't ZFS. ZFS is a copy on write file system. I can assure you fragmentation is indicative of copy on write file systems. I haven't done a study on that, but you can make dollars to donuts. It'll probably be occurring on ZFS likewise if you use it as a backing store. As I said, your SSD solutions, AFAs, won't have this issue. They'll have other issues. After you get done emptying out your bank accounts to pay for the storage, they'll have other issues as well related to lifetime of performance, lifetime of the ability to do writes. And then, like I said, larger OST counts, a little more difficult to do, exhibit. So larger installations and OST counts are more likely to encounter this problem, I suspect, based on what we know, because typically, if you have a very large installation, not all sites, but a lot of sites are trying to run different sorts of jobs through that, and that means different fragmentation and usage profiles, and that probably means you're more likely to see this. I also suspect if you're running in a production environment, you go, wait, the guy from Seagate said fragmentation's evil. We don't see that at our site. Well, you might be seeing it, but you might contribute it to something else. If you've got multiple jobs running against your file system, you might say, hey, that user over there must be using up all my bandwidth, or hey, we must have a bad drive in the system. So I think this contributes to file system performance degradation. It's not the only factor. Unbuffered I/O helps shield you from this as well. So most people don't do direct I/O. Most people do buffered I/O, and they get high variation in the results, but they just chalk it up to luck or someone else using the file system badly, or they call the administrator and say, what's going on? The administrator goes, well, that's the nature of the beast. So impact and performance is more noticeable at higher transfer rates. Block traces provide circumstantial evidence, the deflection curve we talked about. This doesn't consider OST imbalance, bad disk drives, marginal disk drives, bad SSDs if you're using those, bad IV cables. There's other things that can contribute to this problem. And so remediation is highly desirable in my opinion. So in conclusion, we can easily model this in a lab. Study results use a simple model, yield bandwidth impacts from 2 to 35%. Previous efforts have shown a high degree of variation to metadata performance when you have OST fragmentation. So it can affect file creates. That's right, it can affect your file creates. If you fragment your OSTs, that can affect your file creates. At least you get wide variation. Can contribute to performance issues, but it's not the only factor. The impact can vary depending on your utilization patterns. For us at Seagate with our products, we've talked with our core engineering team that work on Lustre to make them aware of our findings and also say we need remediation. We've provided several suggestions to what we think can be remediated and how I'll relate it to Seagate's products. And then instrumentality to help you track this is a longer term development task. This is just the initial study to hopefully generate interest in this issue. But there definitely needs to be some instrumentation produced to help certainly production sites deal with this, and more specifically large production sites. Because if you only got 2 OSTs, you probably don't care. If you got 500 OSTs, you might be caring greatly. That's it. Thank you. Any questions? Here are my 2 email addresses, my Seagate email address and my ACM email address. If you've got questions, comments, tomatoes, whatever. I have questions now.
I'm glad to have John put his contact information up there. We really only have time for a quick question if somebody has one.
So you talked about the tools like Dump 2FS, but have you looked at the file frag utility or the E2 free frag to help you measure that fragmentation, check your methodology? And also, if fragmentation is such a large concern, did you look into using other E2FS tools like E4 defrag?
We did initially look at some of that very initially, but there was more than enough workload here with 2,200 example points and data to collect in 2 months. And so there's more work that needs to be done here. Like I said, this is just an initial effort. Defragmentation related to how you would do online defragmentation with Lustre, if that's really where you're going, that might be a little bit more difficult. That needs a good core engineering evaluation by a Lustre kernel developer, and I'm not one of those. So I can only point out the interesting issues and offer suggestions to people, and we really need the Lustre core people to start to take a look at this. Other questions, potentially, that maybe I can answer, or just stand up here and wave my hands. Yep, thank you. Yep.